every continuous real valued function on a compact space is bounded and attains its extrema. Here we need to consider a compact space and any continuous real valued function on it. And we will need to show that that function is bounded and that it attains its extrema. That is, the function attains both its infimum and supremum. So let us consider a compact space X and a continuous function f from X to R. First we need to show that f is bounded. Let us consider an open interval Jx of the form f of x minus 1, f of x plus 1 for every x element of capital X. From this definition, it is obvious that the point f of x will belong to Jx. And we also let Vx to be the inverse image of this interval Jx under the continuous function f. Since f is continuous and Vx is the inverse image of an open set under a continuous function, hence Vx will be open. And since f of x, the point f of x belongs to this set Jx, x will belong to Vx. Hence we can say that Vx is an open set containing the point small x. Now we can observe that for any point y, f of y will belong to Jx from the definition of Vx. Since Jx is the interval f of x minus 1, f of x plus 1, we will have f of x minus 1 less than f of y less than f of x plus 1. This implies that f is bounded on Vx for every x element of capital X. Now, if we consider the collection of all such sets Vx were x element of capital X, we can see that this is a collection of open sets, and we know that for every x element of capital X, that point x will belong to the corresponding set Vx. So this will be a cover of x also. So this collection is an open cover of x. And since the space capital X is compact, this open cover will have a finite subcover. Say Vx1, Vx2, etc., Vxn. Now we let capital M to be the number maximum of f of x1, etc., f of xn plus 1, and small m is equal to minimum of f of x1, etc., f of xn minus 1. Now, if we consider any point small x element of our space capital X, since this collection Vx1, Vx2, etc., Vxn is an open cover of capital X, we will be able to find an index, say I, such that x element of Vxi, that is x element of some member from this collection. And from the definition of Vxi and the corresponding interval Jxi, we can write f of x will belong to Jxi, that is f of x will lie in between f of xi minus 1 and f of xi plus 1. That is, we have the inequality f of xi minus 1 less than f of x less than f of xi plus 1. But from the definition of small m and capital M, we can write small m is less than or equal to these numbers f of xi minus 1 and f of xi plus 1 is less than or equal to capital M. If we combine all these inequalities, we will get small m less than or equal to f of xi minus 1 less than f of x less than f of xi plus 1, which is less than or equal to capital M, from which we will get small m is strictly less than f of x and f of x is strictly less than capital M. And this inequality shows that f is bounded. Since these constants small m and capital M are obviously independent of the choice of small x, we can definitely conclude that f is bounded. Now it remains to show that f attains its extrema. Since f is bounded, it is obvious that f will have an infimum and a supremum. We will need to show that f attains both its infimum and supremum. For this, let us consider supremum and infimum of f. We assume that L is the supremum and lambda is the infimum of f over x. If possible, assume that f does not attain its supremum L. That is, we assume that there is no point x for which f of x is equal to L. That is, f does not attain this value L. In that case, we will be able to define a new function, say g from x to r, defined by g of x is equal to 1 by L minus f of x. This function will be well defined since this denominator L minus f of x will be non-zero, as we have assumed that for any small x, f of x will be different from L. So L minus f of x is never 0. Hence this function will be well defined, and we can observe that since f is continuous and we can treat L, the constant L, as the constant function, this difference L minus f of x is also continuous, being the difference of two continuous functions. And we can see that the numerator 1 is also a constant function. So g of x is in fact the quotient of two continuous functions. So g must be continuous. However, we can observe that g is unbounded, because if we consider any real number r which is greater than 0, we can see that L minus 1 by r will be strictly less than L. But we have assumed that L is the supremum, that is the least upper bound. That is the least among all the upper bounds. Hence, any real number which is less than L will not be an upper bound of f. So we can say that L minus 1 by r is not an upper bound of f. Hence, we will be able to find a point, say small x, such that f of x is greater than this number L minus 1 by r. Hence, we can also write 1 by r is greater than L minus f of x by simply rearranging these terms in this inequality. And if we take reciprocals on both sides, we will get the reciprocal 1 by L minus f of x will be greater than r. That is, g of x is greater than r. Thus, we have proved that if we take any real number r greater than 0, there will exist a point x such that g of x is greater than that real number. Such an x exists even if r is very large. So, this means that g is not bounded above. But we know that g is a real valued continuous function on the compact space X. And from the first part of our proof, we know that this function should be bounded, being a real valued continuous function on a compact space. It should be bounded. But we have obtained the conclusion that g is not bounded above. So this must be a contradiction. And it shows that our assumption that f does not attain the supremum L must be wrong. So we can conclude that f does attain the value L. That is, f attains its supremum. Similarly, we can show that f attains its infimum lambda as well. Thus, we have proved that f attains all its extrema, and this completes our proof.